Okay, so here's a second example. And now what I'm doing for my numbers I'm adding up, I'm taking the tangent of a random real number between 0 and pi over 2, or in other words, the tangent of a random angle between 0 and 90 degrees. And this is the Archer problem that we looked at a month ago or so, where you're standing 1 meter from a wall, and then you choose a random angle between 0 and 90 degrees, and you fire the arrow, and then you measure the distance from the point on the wall directly opposite from you, and that turns out to be the tangent of the angle. Okay, so first I'm going to run 1,000 trials here, and let's look at the distribution that we see. To make things a little easier to understand, because the distribution is so strange looking, I've looked at our average, which is 5,647. I should have said we're adding up 164 shots, again, distances.
And that's how far it goes on average?
This is how far 164 of them go on average from the original spot.
All right.
What are my numbers here? So mean, so made is 1,000. Okay, so that's my count. The mean, okay. The mean is 5,647, so that's how far away we are on average. So you can see that's right about, here's 10,000.
Yep.
Here's 5,000, that's about where we are on average. The standard deviation is 132,385. So what does that tell you?
So it tells me that there's a lot of variation in this data.
Yeah, the average is 5,600 and the standard deviation is 132,000. Okay. The largest one is 4 times 10 to the 6th, 4.17 times 10 to the 6th. What is that number approximately?
So that's like 4 million.
4 million. And the minimum was 257. And so the distribution looks like this now.
Does not look like a normal distribution. Not at all.
And then if I run it down here, you can see, in fact it's so tall that I can't do it, but you can see I have some at 100,000, I have some out here at 300,000. But I even had, remember we had stuff out at over 4 million.
That's like 1 or 2 of them.
Yeah. So let's run it again. And this time we'll do, instead of 1,000 trials, let's do 100,000 again. Let's see what we got. It's going to take a little bit of time to run. Because last time when we did 100,000 trials, we really started getting a very nice curve. What do you think is going to happen here?
It might. I don't think it's going to develop this any curve at all. I mean, like, you might expect it to look like 1/2 of the bell curve, but I don't think that's going to happen.
Okay, why not?
Well, because, like, see, you already have so many in this column that's just how all of them, just pretty much all of them go there. And then the difference is so large going from this column to the next column. So
okay. In this case, our mean was 1,752, which is vastly different than it was before. The last time the mean was, what, 5,400?
Yeah.
But that's okay, maybe with 100,000 trials it shrinks.
Well, the standard deviation also.
The standard deviation is 55,000. The largest one is now 15 million, 1.5 times 10 to the 7th.
And then the
smallest one's actually about the same. I think it was 227 last time. But let's do one more time at 100,000 and let's see what the mean is.
Alright.
Okay, to see if we're even converging on a mean. What was our mean here? 1,752. Yeah. Let's see if we're converging on a mean. What do you think?
I don't think so.
Alright, why not?
Well, because if the mean changed this much, like from in our other one, the mean stayed pretty much the same.
Yeah.
But we changed from like, what was it before, like 50,000?
5,000.
5,000. We changed from 5,000 to basically 2,000.
Yeah. Essentially, we divided by 3. Okay. So now our mean is with 100,000 trials. This time our mean is 3,536.
Basically double.
And our standard deviation's 300,000.
335,000. Before it was 55,000. So you can see we have a problem here. We're not converging.
Yep.
And if I graph down here against a normal distribution, it just isn't right.
Yeah.
And you can see up here that on 100,000 trials, almost all 100,000 are below 50,000.
It gives you the numbers.
Well,
99,861.
yeah, 99,861 sort of behave nice, but you have this very small number of terribly behaving trials
Just
that
throw everything off.
throw everything off, and they mess with the mean drastically.
Yeah.
So if you have most of your trials are below 50,000, let's say most of your trials were exactly 50,000 even, just so they were at the top of this distribution.
Yep.
But one of your trials was
That.
15
Which it
million.
is.
no,
Or
70
70 million this time.
70 million. That's a lot bigger than 50,000.
Yeah.
Right? So that's not something you're going to see happening with a normal distribution. You're not going to be that far away from the mean. In fact, here the mean is 3,000. The standard deviation is 335,000.
So that's a lot. It's like that's over 200 standard deviations
Right.
away.
So that starts to tell you that this distribution from the Archer game doesn't follow the central limit theorem or the law of large numbers.
Yep.
Well, it does follow the law of large numbers because the mean will eventually converge to the mean of the distribution.
Yeah.
It's just that the mean of the distribution is infinity. So, but that's a little bit more confusing concept.
Yeah.
And so that's what the problem is here. We have this distribution has a mean and standard deviation of infinity, and so the small sample sizes, even 100,000, is small compared to infinity.
Yeah.
Yeah.
So we have a problem here. So I just wanted to illustrate for you that this is a little bit more difficult than some of the simple exercises in your book.
Yeah.
In order for things to converge like this, they have to have certain properties. And flipping coins and picking numbers at random or picking choices at random on a multiple choice test all have the properties that make things converge nicely. But not everything does.
Not everything.
All right. Good work this morning, guys.